Welcome to the Deep Dive, where we plunge into complex research and emerge with the essential knowledge shortcut tailored just for you.
Today, we are immersing ourselves in, well, a really fascinating and rapidly evolving branch of material science. It kind of connects the grocery store right to the operating room.
We're talking about oleogels.
Exactly, oleogels.
That's right. Our mission today is to understand how these ingenious, semi-rigid systems, basically liquid oil that's stabilized into a solid, structured network using really low concentrations of a gelling agent, how they're solving major formulation challenges.
Yeah, quite something.
We received sources covering everything from their fundamental polymer chemistry, specifically ethyl cellulose or EC oleogels, all the way to their groundbreaking use as fat substitutes, which is interesting enough.
Right.
But now their high-impact move into advanced biomedical applications. That's where it gets really compelling.
It really does.
Mhm.
And what's fascinating here, I think, is how the engineering necessity of restructuring liquid oils for food, things like replacing saturated fat in baked goods or maybe processed meats, that whole challenge has inadvertently provided the exact foundational knowledge we needed for sophisticated medical treatments.
It's like a tech transfer we didn't plan.
Pretty much. Oleogels are critical because they are just the perfect vehicle for carrying lipophilic or oil-loving active compounds.
Things that don't dissolve in water.
Exactly. And this capability is absolutely essential for delivering certain nutraceuticals, sensitive probiotics, and also topical drugs that just, well, they dissolve poorly or they're unstable in traditional water-based systems.
It's a classic example, isn't it? A technology pivot. We learned how to control structure for, say, better texture in food.
Yeah.
And suddenly we realize we've mastered a drug delivery mechanism. Okay, so let's start where the application is having maybe the most immediate life-changing impact. Using oleogels as a superior base for topical treatments, specifically in the really difficult area of advanced wound healing, things like severe burns.
Yeah, this area addresses a massive clinical need. If you think about second-degree scald burns, they're not superficial.
No.
They penetrate down into the dermis, they cause prolonged and dangerous inflammation, a really severe risk of infection, and critically, they obliterate the epidermal barrier.
Your skin's natural seal.
Gone. And then this leads to massive, unrelenting transepidermal water loss, or TEWL as it's called. Controlling that water loss and the infection risk is just paramount.
And the sources highlight that the traditional, clinical gold standards like silver sulfadazine, SSD,
Sure.
they actually come with serious drawbacks.
They do. SSD is effective against infection, sure, but it can actually delay the healing process itself.
How?
Well, SSD is known to inhibit the proliferation of fibroblasts.
Okay, and fibroblasts are the cells that rebuild the tissue.
Exactly. They're responsible for producing collagen
Yeah.
and the extracellular matrix needed to build new dermal tissue. So inhibit them, and you slow down the fundamental repair work.
So researchers needed a new base, something that could provide that barrier protection without hindering the cellular recovery.
Precisely. And this prompted a large-scale investigation into plant-based formulations, specifically pairing oleogels with known wound-healing botanicals.
They didn't just test these casually either. I was struck by the rigor of this study. Can you describe the model they used?
Certainly. They employed a highly standardized rat scald burn model. That's crucial for reproducibility, to really prove efficacy.
Right.
They used a specialized 3D printed device called the Rapid 3D, which made sure the dorsal skin of the Wistar rats was uniformly exposed to boiling water, 100 degrees Celsius, for exactly 8 seconds. Very precise.
Ouch. Okay, so consistent injury. And they tested 21 different formulations.
That's right. 21 different topical formulations.
So we have a benchmark, a reproducible severe burn. Now, let's look at the crucial comparison. How did the oleogel base perform against the standard hydrogel base?
The difference was profound, really quite striking. The oleogel bases were typically made using glycerol dibionate. It's marketed as Comprityl 888 ATO as the gelator, usually at about a 20% concentration.
Okay.
And this was immobilized within natural oils like olive oil, sunflower oil, or isopropyl myristate. These oleogels demonstrated significant measurable advantages over the hydrogel basis.
Let's break down the barrier function first, because that TEWL, that water loss mitigation, seems key for minimizing scarring and speeding recovery.
Absolutely. The oleogels were vastly superior just because of their intrinsic lipid-rich nature. They immediately formed this continuous, occlusive lipid barrier on the surface of the wound.
Like a waterproof layer.
Essentially, yes. And this structure not only enhances the absorption of any lipophilic active compounds you might add,
Like the plant extracts.
right, but most importantly, it dramatically slows down water evaporation from the damaged tissue. The result was really evident by day 21 of treatment.
Okay.
The Oleogel treatments achieved near normal skin hydration levels. They averaged around 50 units on the measurement scale they were using.
And the hydrogels?
They lagged noticeably. They only reached about 45 units. And the untreated control wounds were lowest, struggling down around 30 units.
Yo, that 50-unit mark is basically skin that's recovered its ability to regulate moisture. A 5-unit difference between the oleogel and hydrogel base, that sounds huge in clinical terms. It represents a much healthier recovery environment.
It is huge, absolutely. That difference translates directly into lower inflammation and just a better platform for cellular migration, for healing.
Yeah.
But the second major finding was perhaps even more surprising: intrinsic infection control.
Intrinsic, you mean the base itself, even without an added antimicrobial agent, fights infection?
That's what the evidence suggests, through exclusion, basically. Histological analysis looking at the tissue structure under a microscope showed microbial colonies developing on the blank hydrogel-treated wounds.
So just the hydrogel base alone?
Yes. Being mostly water, it provided a pretty welcoming environment for opportunistic microbes. It makes sense.
Okay.
But in stark contrast, on the blank oleogel-treated wounds or on those where plant extracts were added to the oleogel, no microbial colonies were observed whatsoever. None.
So just the physical presence of that lipid barrier, by severely restricting the availability of water right at the wound surface, it's inhospitable to microbial growth.
Exactly. It inhibits the water activity that pathogens need to proliferate. So this means the oleogel base provides an inherent sort of built-in resistance to microbial colonization. It gives the wound a critical initial advantage over infection that a water-heavy hydrogel base simply cannot provide.
That's phenomenal. Really powerful. But, okay, the real acceleration in healing comes from the active compounds, the botanicals. Which of those 21 plant extracts, when they were put in the oleogel base, delivered the best therapeutic outcomes?
Two specific oleogel formulations really stood out, and they worked through distinct mechanisms of action. The first one was the formulation containing Boswellia serrata.
Frankincense.
That's the one, frankincense. The Boswellia oleogel significantly accelerated overall wound closure, and it showed pronounced healthy granulation tissue formation.
Granulation tissue. That means it's speeding up the deep structural repair, filling in the wound.
Yes, precisely. And this aligns perfectly with what we know about Boswellia's mechanism. It enhances fibroblast proliferation and collagen synthesis. So it's essentially building the scaffold of new tissue faster.
Okay, that's one. What was the second star performer?
The second was the oleogel containing Ocimum basilicum. Basil.
Interesting.
Yeah. This formulation resulted in superior epithelialization, that's the final closure and sealing of the skin surface, and it also accelerated fibroblast migration. Its success seems linked primarily to its well-documented antioxidant-mediated wound healing role.
So it fights oxidative stress, which can slow down recovery.
Exactly, it mitigates that stress.
Right.
So this research really establishes a powerful pathway. You combine a protective, intrinsically resistant lipid barrier oleogel base with targeted botanical compounds. It offers a clear mechanism-based alternative to traditional treatments that often rely on heavy antimicrobials that can sometimes compromise the very healing processes they're trying to protect.
Okay, so for topical treatments, the challenge is forming a barrier. But moving inside the body, the challenge becomes, well, surviving an acid bath and enzymatic assault.
That's a good way to put it. Internally, oleogels are proving crucial for protecting sensitive cargo, specifically live bacteria used as probiotics.
Probiotics, things like Lactobacillus reuteri, they offer massive potential, but they have a famously short shelf life and an incredibly difficult journey through the gut, don't they?
Absolutely. The hurdle is twofold, really. First, to be effective, probiotics have to deliver a minimum number of viable cells, usually around 1 million per dose, all the way to the large intestine.
That's a lot of cells to keep alive.
It is. And second, the environment of the stomach and the early small intestine, the duodenum, it's just lethal to them. You got hydrochloric acid in the stomach, potent bile salts in the duodenum. They're designed to kill bacteria and break down lipids.
So the cargo, the probiotics, must be protected until they reach the desired destination, which is further down, the ileum and the colon.
Correct.
And this is where the specific structure of the ethyl cellulose oleogel comes into play again, creating a kind of time-release bunker.
That's a great analogy. Ethyl cellulose, or EC oleogels, have this uniquely strong retarding effect on lipolysis. That's the digestion of fat, particularly in the small intestine.
How does it slow it down?
Well, when the oleogel structure is intact, the polymer strands physically entrap the oil. They prevent digestive enzymes, lipases, and also the bile salts from easily accessing the bulk of the oil. It dramatically reduces the surface area available for that enzymatic reaction.
Can we quantify just how robust this protection is? Is there data on that?
Oh yes, there's very clear in vitro evidence that models this aggressive digestive environment. Researchers developed a modified lipolysis model, and it was designed to fully digest pure medium-chain triglyceride oil, MCT oil, which digests really fast in about 120 minutes.
Okay, so a tough test.
A very tough test.
Yeah.
Now, in that same aggressive enzyme-rich model, a stiff EC oleogel formulated with 10% ECI, it resulted in less than 50% lipid digestion over the entire 120-minute period.
Wow, less than half digested in 2 hours when the pure oil's gone.
Exactly. Pure MCT oil would reach 50% digestion in just minutes.
That's a staggering difference.
It is. The oleogel slows the process down from minutes to hours, and that provides the essential temporal window for the cargo, the probiotics, to pass through the hostile upper GI tract relatively unharmed.
Okay, protection is critical, but as you mentioned, control is the next step. It's useless if the capsule, dissolves in the stomach,
Right.
but it's also useless if the capsule is so strong it just passes straight through without releasing the payload in the right place. How do scientists tune the release profile to specifically target the colon?
This is where some really advanced quantitative modeling comes in. They successfully applied the PEPIS model. It's a well-established quantitative tool in drug release kinetics, and they used it to analyze the complex process of fat digestion within the oleogel matrix.
The PEPIS model, for those of us not familiar, what does it actually tell us about release?
So the PEPIS model looks at how a substance is released from a polymer matrix. Release kinetics are typically governed by, well, three main things. Diffusion, that's the movement of the drug through the network. Erosion, the polymer network itself dissolving. And in this case, crucially, enzymatic reaction, the lipolysis. The PEPIS model cleverly groups these complicated kinetics using an exponent, which is labeled N.
Okay, an exponent n. What does the value of n reveal about the mechanism?
Well, if the exponent N is around 0.5, it suggests something called Fickian diffusion, basically a steady, concentration gradient-driven release. Kind of predictable.
Right.
But high-end values, particularly those greater than 1, which get categorized as type D, they're the key here. This high-end value indicates a release mechanism dominated by disintegration-limited digestion.
Disintegration limited. Okay, so the rate of release isn't just about slow molecular movement. It's controlled by how fast the physical structure falls apart.
Precisely. If N is greater than 1, you're moving into a regime known as super case 2 transport. It basically means the structural failure of the matrix itself is the rate-determining step.
And that's what researchers want to achieve in the colon.
Exactly. They want the matrix to hold firm in the duodenum where N would be low and diffusion is slow, and then they want it to suddenly fail or disintegrate in the colon, leading to a high N.
So how do you actually engineer an EC oleogel that's stable enough to survive the stomach and the duodenum, but then intentionally fragile enough to disintegrate almost on command in the lower GI tract?
That is achieved by incorporating specific excipients, specific additives, into the EC oleogel structure itself. And these are hydrophilic powder disintegrants.
Hydrophilic meaning water-loving.
Yes. They're typically food-grade, highly wettable powders, things like certain modified starches or maybe cellulose derivatives. They are designed specifically to attract water.
And since the colon is a highly aqueous, watery environment, they essentially act as internal Trojan horses.
That's a perfect description.
Exactly.
As the oleogel moves down to the lower GI tract, these hydrophilic powders rapidly suck up water and swell when they contact that high water content environment. This swelling creates massive internal stress within the oleogel structure. It causes the polymer and oil matrix to physically fracture and break apart.
So it triggers the breakdown.
It triggers the breakdown. This targeted structural failure releases the protected probiotic payload rapidly and effectively, right at the precise location where you want it.
Wow, that's the ultimate proof of control, isn't it? It allows for this precise tuning of EC oleogels, maintain a low, slow release profile in the hostile upper GI tract,
Right.
and then achieve a high rapid disintegration limited release, high Mn, exactly where you need it in the ileum and colon. This is moving far beyond simple encapsulation. This sounds like molecular targeting.
It really is approaching that level of precision.
Okay, so the success we've discussed both in, wound care and in this targeted GI delivery, it relies entirely on the specific structural traits of ethyl cellulose. To really understand these applications, we need to unpack what makes EC the polymer of choice for gelling oil in the first place.
Absolutely. We need to get into the fundamentals.
Yeah, EC is everywhere, right? I mean, in food, pharmaceuticals, why is it such a dominant gelling agent specifically for lipids, for oils?
Oh, EC is a real workhorse for several key reasons. Firstly, it's derived from cellulose, which is, the most abundant polymer on Earth, so it's highly available and relatively inexpensive.
Okay, practical reasons.
Very practical. And crucially, it has GRAS status, generally recognized as safe or near food grade status across most of the world. That means it's biocompatible and safe for ingestion. Big plus.
And how does it physically structure the oil? It's not like gelatin or agar, which work in water.
No, the mechanism is entirely different. EC forms what are called thermoreversible gels.
Thermoreversible, meaning heat makes it liquid, cooling makes it solid.
Basically, yes, and you can cycle it. You start with the EC powder, and you have to dissolve it in the liquid oil. Now, this requires heating the mixture significantly, typically above its glass transition temperature, which happens around 130 degrees Celsius.
That's quite hot.
It is. And EC is soluble in oil only when it has a specific degree of substitution. That's a chemical modification term, usually between 2.4 and 2.5 ethoxyhydroxyl groups per glucose molecule on the cellulose backbone.
Okay, so you heat it up high, dissolve it, essentially liquidizing the polymer in the oil. Then what happens when it cools down?
As the temperature drops, the EC polymer strands start to self-assemble. They form a three-dimensional, semi-rigid network throughout the oil.
What holds the network together?
It's stabilized primarily by hydrogen bonding among the residual ethoxy and hydroxyl groups on the polymer chains, and also weaker van der Waals forces. This network then traps the liquid oil within its pores, and that's what gives the whole system its semi-solid texture.
The sources point to two main factors controlling the resulting gel strength, how hard it gets. First, the molecular weight of the EC polymer itself.
Right.
And second, the chemistry of the oil being used. Let's start with the polymer.
Okay, so the molecular weight essentially determines the length of the polymer chain. EC is commercially sold in various viscosities, often measured in centipoise or CP. You see grades like 10 CP, 45 CP, or 100 CP.
Higher number means longer chains, higher viscosity.
Generally, yes. And researchers tested this using a technique called back extrusion. It's a mechanical test where a probe measures the force required to penetrate the gel.
Okay.
And the results were really categorical. Higher molecular weight EC, like the 100 CP grade, produces substantially harder, firmer gels compared to the lower molecular weight ones, like 10 CP.
That makes intuitive sense, I suppose. Longer strands could create a denser, more entangled web, maybe.
That's the intuitive picture, yeah.
Yeah.
But then there's the oil type factor, which is also really interesting.
How does the type of oil affect the gel strength?
The fatty acid composition of the liquid oil has a dramatic structural effect. It turns out that oils with a high degree of unsaturation, meaning they have more double bonds in their fatty acid chains, produce much firmer gels.
Really? Give me an example.
Okay, so take flaxseed oil. It has a very high level of polyunsaturation, around 59% linolenic acid, which has 3 double bonds.
Right.
Flaxseed oil creates significantly harder EC gels compared to, say, canola oil, which is mostly monounsaturated, around 62% oleic acid with only 1 double bond.
But wait a second. If the EC polymer is what's forming the network structure, why should the internal chemistry of the oil trapped inside matter so much for hardness?
This is where the prevailing structural hypothesis comes in. The idea is that the unsaturation level of the fatty acids dictates how efficiently the oil molecules can pack within the voids, the pores, of the polymer network.
Tighter packing makes it stronger.
That's the theory. Tighter packing leads to a higher molar density of the oil within those pores. This better packed oil provides more effective support for the polymer network, resulting in a firmer structure overall. It's not that the oil is chemically bonding to the polymer.
Okay.
It's more that the oil's inherent shape and how it packs optimizes the space within the scaffold, enhancing the overall rigidity of the whole system.
It sounds like this invisible, almost coral-like scaffold supporting a highly organized liquid phase. How do researchers actually confirm this microstructural arrangement? How do they see it?
Visualizing this structure is notoriously difficult. Most conventional oil gelators, like waxes for example, display something called birefringence when you look at them under polarized light. It makes them easy to see microscopically.
But EC doesn't do that.
No.
Hmm.
After EC oleogels are made using that high heat process, any crystallinity that might have been present seems to disappear. They become isotropic.
So if standard light microscopy is out, what technique did they have to use to actually expose the structure?
They had to rely on advanced cryoscanning electron microscopy, cryosem.
Cryo means frozen, right?
Exactly, and this technique requires really meticulous preparation. The sample has to be cryofixed, frozen extremely rapidly, usually in liquid nitrogen slush, to prevent ice crystal damage, which would destroy the delicate structure.
Okay.
And then comes a critical step. The liquid oil has to be removed to actually expose the underlying polymer skeletons so you can image it.
How on earth do you remove the oil without collapsing that fragile network structure?
Carefully. They use a solvent extraction technique. They typically drip a specific solvent, often isobutanol, over the frozen fractured surface of the sample.
Why isobutanol?
It's carefully chosen because it's a good solvent for the liquid oil, so it allows the oil to dissolve and wick away.
Oh.
But it's a poor solvent for the EC polymer itself. This means the underlying scaffold remains intact and stable for imaging by the SEMS.
Clever. And what did those detailed images of the exposed scaffold actually reveal? What did it look like?
They reveal this distinctive, continuous, coral-like network. It was composed of interconnected polymer strands or maybe bundles of strands. This network clearly surrounded the oil pores, which typically measured somewhere between 3.0 and 4.5 micrometers in size.
The visual confirmation, the EC polymer definitely created the required three-dimensional structure.
Yes, it provided that crucial visual proof.
Okay, but here is where the science gets really challenging, doesn't it? Because these structural findings lead directly to an unresolved paradox concerning the gel's rigidity.
Absolutely. This is where it gets really interesting. The paradox is clear. We know from the mechanical tests, like back extrusion, that the polymer's molecular weight drastically changes the mechanical properties. 100 CPEC makes a much harder gel than 45 CPEC.
Right, we established that.
Yet subsequent cryosesamem studies, careful measurements from those images, show that oleogels made with 45 CPEC and 100 CPEC, despite having significantly different measured hardnesses, they showed no measurable difference in their average pore size. The holes were the same size, statistically speaking.
Yeah, that raises a critical question then. If the mechanical strength changes so drastically based on the length of the polymer chain,
Yeah.
but the physical size of the void space holding the oil doesn't change, what is the mechanism governing the mechanical strength of the gel? It can't just be pore size.
Exactly. It implies that the mechanism isn't simply related to how big the oil pores are. Instead, the molecular weight, the chain length, must be affecting the characteristics of the strands themselves forming the network.
How so?
Well, researchers hypothesize that maybe higher molecular weight polymers lead to thicker fiber bundles, or perhaps a higher degree of entanglement between the chains, or potentially even a more complex fractal dimension of the network structure that just hasn't been properly quantified yet.
So the bottom line is,
The bottom line is our fundamental understanding of exactly how the EC network confers rigidity is still incomplete. It clearly demands future studies using maybe high-resolution rheological mapping or more advanced network analysis techniques to figure it out. It's a fascinating puzzle.
okay, if we connect this microstructural understanding, including the puzzles, back to the broader applications, it's really clear that EC oleodiols are at the forefront of this massive effort to structure liquid oils, not just for food texture, but to deliver essential bioactives, moving far beyond just burn cream or probiotics.
Absolutely. This is really the era of functional oils. Stabilizing the oil phase like this allows us to use it to protect compounds that are otherwise, metabolically unstable or poorly water-soluble. We can turn them into highly effective nutraceuticals.
Curcumin is a prime example mentioned in the sources. Huge therapeutic potential, but incredibly difficult to deliver effectively in the body. How did oleogels help there?
Right, curcumin is highly promising, but its really poor water solubility and incredibly rapid metabolism severely limit its bioaccessibility, basically, how much the body can actually absorb and utilize from a dose.
So it gets broken down too fast.
Way too fast. But when it was encapsulated in an oleogel, studies showed significant improvement. Oleogels enhanced curcumin bioaccessibility up to 80% in one particular study, and they also dramatically improved its oxidative stability, shielding it from degradation before it even got absorbed.
Does the type of gelator structure matter here? I mean, are all oleogels created equal for delivering something like curcumin, or does the specific network like EC versus maybe a wax make a difference?
Oh, the structure matters tremendously, especially for the release timing.
Hmm.
Researchers compared different types of oleogens, not just EC, but others formed by waxes or other crystalline systems. And they found something really interesting.
So was that?
Highly ordered crystalline networks, the kind formed by things like monoglycerides or rice bran wax. They actually resulted in lower curcumin bioaccessibility during simulated in vitro digestion.
Lower. Why would a more ordered crystalline structure be less effective at releasing the bioactive compound? That seems counterintuitive.
It does at first glance, but the hypothesis is that the dense, tightly packed crystalline particles physically hinder the release of the encapsulated molecules. They sort of trap the curcumin as the digestive enzymes, the lipases, try to break down the surrounding oil.
Okay, so the crystals get in the way, essentially.
Yeah.
In contrast, more amorphous networks, those lacking that long-range crystalline order, like the kind formed by EC, or another example studied was a mixture of zolicidosterol and dolisinol, these resulted in much higher bioaccessibility, almost comparable to just delivering curcumin in non-structured liquid oil.
So the amorphous structure, like EC's coral network, breaks down in a way that allows the bioactive compound to escape much more freely during digestion.
That seems to be the case. It suggests the breakdown is more uniform or accessible, so it's a crucial design parameter. You have to
Right.
optimize the gel structure not just for physical hardness or stability, but for the specific release kinetics required for your particular cargo.
Right. Which leads us, I think, to the most complex system described in our sources, really pushing the engineering boundaries.
Yes. We're talking about the ultimate feat of nanoengineering here, the water in oleogel and water emulsions. WOW
Okay,
emulsions.
break it down. Water in an oleogel. In water. Exactly. These are highly sophisticated, multi-layered systems. You encapsulate a primary water phase, tiny water droplets, inside a structured oil phase, the oleogel,
Mm-hmm.
which is then dispersed as larger droplets within an external continuous water phase.
Wow, why go to all that trouble? What are they used for?
They serve two primary functions generally. One is sometimes reducing the overall fat content in a food product by replacing some of the bulk oil with structured water.
Okay, fat reduction.
But more importantly for our biomedical focus, they're used to protect highly sensitive, water-soluble compounds that you want to deliver, things that couldn't survive in the oil phase alone.
How does the oleogel structure provide the key benefit in this complex triple-layer system?
The solid fat network, the oleogel structure within that middle oil layer, is absolutely critical. Its main job is to increase the tortuosity of the paths for molecular transport.
Tortuosity. Okay, technical term. What does that mean in practice?
Think of it like this. Tortuosity is the ratio of the actual winding, difficult path length a molecule must travel to get from point A to point B compared to the simple straight line distance between those 2 points.
So the more obstacles and twists and turns, the higher the tortuosity.
Precisely. A simple liquid oil layer is pretty easy for small molecules to diffuse through quickly, low tortuosity. But a semi-solid oleogel layer, with its dense interconnected network of solid EC strands, forces molecules to navigate a much longer, denser, winding maze.
Ah, I see. So it dramatically reduces the diffusion kinetics. It slows everything down.
Dramatically. And this high tortuosity structure does two key things. First, it physically prevents or slows the leakage of the sensitive cargo held within those internal water droplets.
Like water-soluble vitamins or maybe even probiotics.
Exactly, things that might otherwise leak out into the oil phase or even the outer water phase too quickly. The source is mentioned using manganese ions in diagnostic models as an example. Second, the oleogel provides critical mechanical strength. It helps the dispersed oil droplets resist osmotic forces. These forces can occur when the emulsion moves between environments with different salt concentrations, like in the GI tract, which could otherwise cause the internal water droplets to swell and rupture.
So it holds everything together physically and slows down unwanted release.
Yes. And researchers have even built WOW systems using specialized semi-solid fats for that middle oleogel layer, allowing for a temperature-triggered release.
How does that work?
The fat crystals in the oleogel are designed to melt sharply above a certain threshold temperature. When they melt, The network structure collapses, the tortuosity plummets, and the entrapped water-soluble compound is rapidly released.
Potentially triggered by body temperature, for instance.
Potentially, yes, or an externally applied heat source.
It is truly incredible to realize that the fundamental polymer science maybe originally figured out to ensure a better mouthfeel in a low-fat sausage
Ah, yeah, possibly.
is directly transferable and now being engineered for these highly sophisticated, targeted internal drug delivery systems that can respond to minute temperature fluctuations inside the body.
It really speaks volumes about the universality of material science principles, doesn't it? The physical mechanics of structuring a liquid oil, whether you're doing it for rheological function in food or for controlled, localized release in medicine, it's all rooted in establishing a robust and controllable 3D network.
Well, this deep dive has certainly shown how the technical progress with EC oleogels and oleogels in general is dramatically improving the therapeutic delivery landscape. It's solving challenges that traditional water-based systems simply couldn't touch.
The technical progress is undeniable, absolutely. However, our source material also revealed something else, a deeper, still unresolved question. And it stems from concurrent research back in the traditional food science world, specifically meat science. Yes, and this question has potentially profound implications for how we fundamentally understand biological structure stability in general. And it's relevant because it challenges some of the decades-old theories that actually underpin oleogel-based food design, too.
Okay, you've got my attention. What's the question? You're referring to the classic model of stabilizing fat in comminuted meat products, right? Like sausages or frankfurters.
Correct. The classic understanding for decades has been that fat globules in these products are stabilized by something called interfacial protein films, or IPFs, thin films of protein that supposedly form around the fat droplets.
And these IPFs are believed to reduce surface tension and prevent the fat globules from coalescing and leaking out during cooking, what's known as fatting out.
Exactly. That's the textbook model. But this entire model relies on a critical, long-held belief that specific proteins, particularly muscle proteins like myosin, bind directly and preferentially to the lipid surfaces. They like the fat more than the water phase.
Okay, seems logical, but
But when researchers tried to rigorously verify this preferential binding using modern, highly sensitive techniques, the results were, well, inconclusive at best.
they couldn't prove the binding.
They struggled. When they used cutting-edge nanoscale techniques like surface plasmon resonance, SPR, which measures tiny changes in mass at a surface, or UV spectrophotometry, looking for protein concentration changes at the interface, they consistently failed to demonstrate the expected strong binding affinity.
Even when they tested purified myosin against purified lipid surfaces.
Yes, whether the protein was heated, not heated, different fat sources, the change in mass or absorbance measured at the interface was minimal, sometimes non-existent. The expected preferential binding just couldn't be conclusively proven with these sensitive methods.
Wow. Okay, that is utterly disruptive. If the protein films we see around fat globules aren't the result of preferential stabilizing binding,
Yeah,
then what are they? And maybe more importantly, how does the fat stay stable in these products?
right. And this leads directly to the provocative thought we wanted to leave you, the listener, with today. What if?
Hmm.
What if these interfacial protein films, these IPFs we talked about for so long, are not a stabilizing feature at all? What if they are simply a defect? Or maybe a deformation caused purely by the difference in heat capacity between fat and protein?
Explain that. How would heat capacity cause a film?
Well, during the cooking process, the fat globules, having a lower heat capacity, will heat up faster than the surrounding aqueous protein matrix.
Okay.
So the protein immediately adjacent to the hotter fat globule could denature and solidify, forming a thin shell, faster than the bulk protein matrix further away. This would create a thin, visually distinct layer surrounding the fat.
That looks like a film.
That looks like a film, but it might not be formed by preferential binding at all. It might just be an artifact of uneven heating, a zone of faster denaturation, and it might not even be particularly stable structurally.
So, the structure we've potentially based decades of meat science, emulsion science theory on the IPF might not be a functional mechanism of stability, but merely an artifact of the rapid localized heating process itself.
That's the provocative question, yes.
Huh.
If IPFs are proven to be heating artifacts rather than functional, preferential stabilizing films, it fundamentally challenges how we think about engineering stability in many fat-containing biological systems, including foods designed with oleogels.
Hmm.
It forces us to ask, what other fundamental biological or food structures, which we currently assume are stable due to specific molecular interactions, might actually turn out to be just visual artifacts caused by processing conditions like heating or shear?
A fascinating and potentially revolutionary question to mull over, something to explore on your own.
Indeed.
That wraps up our deep dive into the solid future of liquid oils, stretching all the way from the lab bench to the pharmacy shelf and maybe even questioning some things back in the butcher shop.